We've had a few different circuit elements that we've considered so far. One was just a battery. One was just a wire. Just a straight conducting wire. We've had resistors, which get this symbol. And we did a lot of work analyzing circuits with different arrangements of resistors. However, these are not the only things that we can put in a circuit. So the battery creates a voltage difference, the wire conducts electricity, the resistor provides some resistance. However, there are circuit elements that do other things. One of those other things is store charge. So an object that stores charge is called a capacitor, and it gets a slightly different symbol. It looks kind of like a battery, except the two lines are exactly the same length. So this is known as a capacitor. And a capacitor has the capacity to store charge. So if I have a part of my circuit where the charge is going to get stuck, connect the circuit, I connect all my wires to the battery, and there's some place where charge starts to build up, that's going to be known as a it's going to have some capacitance, is what we would say. So a capacitor has some capacity for storing charge, which is why we call it a capacitor. So here's a type of capacitor. We've already seen this. This is known as a set of parallel plates. We call it a parallel plate capacitor. And depending on how big these plates are and how far apart they are from each other, these plates can store more or less charge. So what determines, or what defines an object's capacity for storing charge? Well, it turns out that's fairly simple to write down. So if I want to know an object's capacitance, it's defined in this way. It's going to get the symbol C. And an object would have more capacitance if it took on a lot of charge, even if you only applied a small amount of voltage to that object. So if my parallel plates over here, if they could store a lot of charge, even if I only connected a small voltage battery to it, we would say that these have a large capacity for storing charge, or a large capacitance. So what we can do is we can just say it's the amount of charge you get, the change in charge on the object, for a given voltage. Oops. For a given voltage. If I apply a voltage difference between those two different plates, they are going to get a certain amount of charge that gets stuck on those plates. And that will tell me how much capacitance it is, just based on the amount of charge you get for a given amount of voltage. Now, let's see how that would work schematically. Let's say you have a battery. The battery comes over here to my parallel plate capacitor. So the battery provides some voltage given by its EMF. The capacitance is going to be, I should say this is the voltage drop across the capacitor. My capacitor has some capacitance associated with it. What will happen is that for a very short amount of time, there will be a little bit of current that comes down, but the charges cannot jump across the gap in the capacitor. If I connect my two parallel plates to a battery, the positive charges will start to build up on a plate, but they can't get across to the other side. So we'll start to build up charge here. and it will start to build up negative charge on the other side, because any positive charge that builds up over here had to leave some negative charge behind somewhere, and that negative charge is just going to accumulate on the plate. Now, an important point about this is eventually, and very quickly I might add, almost instantaneously for this circuit, the current is going to be zero. You connect it, the plates charge up really quickly, and we can't have any more current. The reason being, if I did have current in the circuit, that would mean I'm forcing more positive charge onto the plate. And as we build up more and more positive charge, it gets harder and harder to put more positive charge on, because the positive charges that are already on the plate are going to repel any other positive charges that are going to be coming forward. So they're going to push those back, and eventually they're going to push back so much that the current is just going to stop. So once we reach the maximum capacity, once we've got our fill of charge, or delta Q, there's going to be some buildup of charge, which I'll call delta Q. It's going to be positive on this plate, negative on this plate. Once the capacitor is filled to capacity, the current is going to stop. What determines an object's capacity for storing charge? Well, really, remember, capacitance is related to how much charge the object can store. Now, we can have capacitors in any variety of shapes and materials. But at the end of the day, this defines what the capacitance is. However, if we're asking what actually determines for a given object its capacitance, a lot of it has to deal with geometry. Let's take the case of parallel plate capacitors. Okay, so I've got two plates here, and let's say the plates each have an area A, and let's say they're separated by a distance d. Well, if I connect these plates to a battery, charge is going to start to build up. So let's put some charge in on there. Maybe I get some positive charge on this plate, some negative charge on this plate. Charge is built up. Now I want to relate the shape of these plates, the geometry of these plates, to its capacity to store charge. Now we would expect that the capacitance of these parallel plates would be larger, would have a bigger capacity to store charge if the plates just had more area, more places to put the charge. So capacitance will increase with the area. Additionally, if the plates were really close together, so if D was very, very small, then I wouldn't really be separating the positive and negative charges by that much, and it wouldn't take that much energy to pull them apart, because they'd still be fairly close. So we'd expect that as D gets smaller, we have more capacity to store charge. To take that into account, we're going to just take A divided by the distance between the plates, the area divided by the distance between the plates. The other thing that's going to make a difference, so there's some electric field between these plates. And depending on how easy it is to form that electric field, it'll make it easier or harder to create these, put charge on the capacitor plates. So I need some parameter that tells me how easy it is to generate electric field between those plates. It turns out we have a parameter called that. It's called the permittivity. We've seen permittivity once before. In that case, we saw the permittivity of free space, which is the permittivity of vacuum, which is pretty much the same as the permittivity of permittivity of air, because air is very close to vacuum. But if I put other materials in here, suppose I put a piece of plastic or a piece of wood or some other material inside my capacitor plate, I would have to put a different permittivity to correspond with that material. So this is what's going to determine the capacitance. It's going to be determined partly by the geometry, and for parallel plates, we can write it this way. I should say that this is the capacitance for parallel plates only, so I'll write it as the capacitance of PP for parallel plates. It's going to be determined by the geometry, so the area, the distance between the plates, and also what material is between the plates. How difficult is it to generate an electric field between those plates? When we reintroduced circuits, I said that our new mantra for this section was going to be where are charges flowing and where is the energy flowing. So we can take into account how charges are flowing by looking at the resistance and the capacitance, because for resistance that will restrict but not completely stop the charge flow. And capacitors will actually completely stop the charge flow. The charge will start to build up on the capacitors. But we have not yet talked about what capacitors are going to do to the energy. So we also want to figure out how energy is going to flow. We know how to do that for resistors. We don't yet know how to do that for capacitors. One of the nice things about capacitors is that it's fairly easy to describe how much energy gets stored inside a capacitor. So unlike a resistor, which will dissipate the energy in heat or light or whatever it happens to be, it's a light bulb, capacitors store the energy in the form of electric potential energy, because the charges get built up and they don't go away anywhere. They just stay on the capacitor. So we want to write the formula for the potential energy stored in a capacitor. And we would expect that if a capacitor has more charge, then it would get more potential energy. And that is in fact the case. So the more charge we get, I'm actually going to write delta Q squared. So however much charge we get on the capacitor, I'll call this plus delta Q, bottom plate will be minus delta Q. The energy will be related to the amount of charge we get. Furthermore, it will be related to the capacitance. Now, if we have a big capacity for storing charge, then it doesn't really take that much energy to put charge on the capacitor. If we have a small capacity to store charge, then it takes a lot of energy. So the amount of energy we get should be inversely related to the capacitance for a given amount of charge, and that's exactly correct. Now there's this extra factor of 1/2 that comes in there. I'm not going to derive this fully, but we can just trust that there, if you look it up, you'll find that there's an extra factor of 1/2. Now this is not the only way to write the potential energy stored in a capacitor. So this is potential energy in a capacitor. This is not the only way to write that, because again, we have this other formula for capacitance. And just by changing out the variables, by doing the substitution, instead of writing this in terms of charge and capacitance, I could write it in terms of voltage and capacitance, which is easy enough to do. That would be 1/2 C delta V squared. Similarly, I could write it in terms of voltage and charge, which would be 1/2 the charge times the voltage. So we have a few different ways of writing the the potential energy stored in a capacitor. And which one you use is going to depend on what's fixed. Is the capacitance fixed? Is the voltage fixed? Which of these variables do you know? There are a couple of points I would like to emphasize about the difference between batteries and capacitors. So suppose we have a battery here. I have a battery, it's a 3-volt battery as I've drawn it, which means everywhere in this part of the circuit is 3 volts everywhere in this part of the circuit, is 0 volts. And the charge is going to flow through that light bulb emitting light. Well, what we can say about batteries is that batteries create a constant voltage difference. So I plug my battery in, I get 3 volts pretty much until the battery dies. We always get 3 volts. The reason is because we're using some chemical potential difference inside the battery to generate that electric potential, that 3 volts. Difference. An important part about this comes from something that I should emphasize is that nothing is getting charged up here. Batteries, this is a bad part of our lexicon. So in common everyday speech, your cell phone battery dies, you say, oh, I've got to charge my cell phone. With batteries, nothing is getting charged up. You're not building up any charge. So we say nothing gets charged up, not in the physics sense of charged up. Nothing gets charged up in a battery. Nothing gets charged up in a battery. Charge is not being built up anywhere. This is remarkably different than what happens in a capacitor. Let's see how a battery contrasts with a capacitor. What would happen if we really were charging the battery up? Well, in contrast to batteries, capacitors create a non-constant voltage difference. So let's say we charge up our capacitor, and capacitors we really can charge up. Let's say we charge that up with a certain amount of charge, and let's say we give it enough charge to give the same 3 volt difference that the battery had. Well, what we will see is that that 3 volt difference does not last very long, because the charge is going to repel each other. So the positive charges are repelling each other. So they're going to move away from each other. They're going to create a current going around the circuit, just like the battery did. However, these charges repel each other very, very quickly. So the light bulb is going to flash quickly and then go out. Light bulb will flash quickly and then go out. It goes out because as soon as the charges have all repelled each other, as soon as these positive charges have met up with those negative charges, the voltage is gone. There is no more charge built up on the capacitor, and it's done. No more current flows. The circuit's dead, the light bulb turns off. No more light coming out. So if we weren't really charging something up in our batteries, we were really charging them up, those would be capacitors. We're not really charging them up, and it's a good thing because batteries, we want them to last a long time. We can do that through chemistry. We can't really do that with a capacitor. So we talked about the permittivity and how for a parallel plate capacitor, the capacitance is given by the permittivity times the area divided by the distance between the plates. Well, permittivity is one way of representing how a material will respond in a capacitor. There's another way known as the dielectric constant. The dielectric constant can be expressed this way. The dielectric constant is kappa. And if I take kappa times the permittivity of free space, I get the permittivity of the material. Or equivalently, I can write, just by doing a little bit of algebra, that kappa tells you the ratio of the permittivity of the material compared to the permittivity of free space. So I'm just going to write down a few different materials here, and we'll see what their dielectric constant is going to be. So let's see, for vacuum, well, by definition that has to be 1, because the ratio of the permittivity of vacuum to the permittivity of vacuum obviously has to be 1. Let's see, for air, it's very close to 1, but not quite 1. So I've got 1.123, 3 zeros, and then 5, 4. Paper gets a bit higher permittivity. You can see that as I change materials, as I go to thicker and thicker materials, thicker meaning more dielectric constant, not physically thicker necessarily. As I go to those materials, the dielectric constant is only getting bigger. For paper, it's about 3.0. For a cell membrane, it's about 9.0. For water, it jumps up quite a bit. It's about 80. Here's a number I got from the book, strontium titanate. It goes up to about 300. So you will notice that as we go to different materials, the dielectric constant obviously changes. What would happen if we just put a metal in here? Well, in that case, we'd be able to just keep pumping charges on and on forever. Strontium titanate is close to being metallic. But if I could just keep pumping charges on forever, what we'd find is that our dielectric constant would actually be infinite, because I would be able to pump an infinite amount of charge into our capacitor, although at this point it wouldn't be a capacitor, it would really just be a wire. But what we'll find is that vacuum's always going to have the smallest dielectric constant, and as we go to more and more conductive material, it's going to approach larger and larger values of the dielectric constant. I'd like to revisit our mantra for circuits. So we said that when we're solving circuit problems, there's going to be two questions that we're going to be interested in. One, where do the charges go? And two, where does the energy go? If we can answer these questions, then we should be able to answer just about any question thrown at us from circuits. So we want to be able to do this for fairly complicated circuits, circuits that have both resistors and capacitors in them. So we better know what happens to the charges in resistors and capacitors, and what happens to the energy in resistors and capacitors. Let's start with what the charges do first. So if I'm looking at a resistor, we would say that the charges flow through a resistor R. Let's say charges flow through R. Similarly, if we're talking about a capacitor and what the charges are doing, we would say that the charges get stuck on the capacitor. This is why, if I look at the voltage drop across a resistor, it depends on the current, which is the flow of charge, not the actual amount of charge. However, if I look at the voltage drop across a capacitor, that's equal to the charge on the capacitor, how much charge gets put on the capacitor, I'll call it delta Q, divided by the capacitance of the capacitor. So in this case, we are looking at the actual charge. So this is what the charges are doing. These are where the charges go. They either get stuck on the capacitor or they're flowing through a resistor. What about the energy? what does energy do in a resistor? Energy gets dissipated as heat or light, if we're talking about a light bulb resistor, or possibly gets dissipated in other ways. We can write the rate at which energy is transferred, because that's just given by the power in a resistor, which is going to be equal to I squared R. There's other forms of this. We can just rewrite it in terms of Ohm's law. Where does the energy go in a capacitor? Well, the energy is actually going to get stored. It's not going to be dissipated. It's going to get stored as electrical potential energy. As electrical potential energy. And if I look at the amount of energy stored in a capacitor, we said before it's equal to 1/2 the charge squared divided by the capacitance. Again, there were other forms of it that we could determine based on the definition of capacitance. So this is what we want to pay attention to. We're going to be solving circuit problems, and our mantra, the only questions we're really going to be concerned with are where do the charges go, and where does the energy go? I have here a battery that's a 2-volt battery. It's got an EMF of 2 volts. A resistor that has 1 ohm of resistance. And we want to find what's the charge doing and what's the energy doing. That's pretty simple if I just remember Ohm's law and then the equation for the energy stored or the energy dissipated by a resistor. So by Ohm's law, I can write that the current is delta V over R, and plugging in 2 volts for the voltage drop across the resistor, because the voltage drop is going to be the same across the resistor as it is across the battery. And if I plug in 1 ohm for the resistance, you see you will get 2 amperes of current. And if we plug into the power equation, P is I squared R, I would get 2 amps squared would give me 4 amps squared times 1 ohm of resistance will give me 4 watts of power. So I can figure out the rate at which we're using up energy, and I can figure out what the charges are doing. Suppose we take an equally simple circuit, but now instead of a resistor we have a capacitor. Well, again, we want to figure out what the charge is doing. So as always, I can say above the battery, the voltage, if it's a 2-volt battery, we'll say that's 2 volts everywhere over here, and everywhere down here. We'll say 0 volts. So I know the voltage drop across the capacitor. I know that there will be positive charge building up on one side of the capacitor and negative charge built up on the other side. I want to know what the charges are doing and what the energy is doing, so I can figure out what the change of the charge, what the change of the charge on the capacitor is going to be once I connect that battery. And the total charge on the capacitor is going to be, by the definition of capacitance, is going to be C times the voltage drop across the capacitor. So that's going to be 1 farad times 2 volts, which will give me a total of 2 coulombs of charge on my capacitor. Now I know that since there are positive and negative charges built up there, that we have to have electrical potential energy stored within the capacitor. And I can figure out how much energy is stored in that capacitor, again, using the formula 1/2 the charge squared divided by the capacitance. So if I plug numbers in here, the charge squared is going to be 2 coulombs squared, so it's going to be 4 coulombs, 4 coulombs squared, divided by the capacitance, which is 1 farad, divided by 2 should give me 2.0 joules of energy stored within that capacitor. So it's just 2 squared divided by 2 divided by 1. So I get 2 joules of energy stored in that capacitor. So I know how much charge gets stuck on the capacitor and how much energy is stored in the capacitor as well. So we figured out what the charge is doing and what the energy is doing.